好，非常感谢。那么，我相信这不仅是推动着产品的更迭还有升级，同时也为在座每一位企业的发展带来主题演讲是微发泡成型技术的最大化。In the following section, Mr. Michael Prince, CEO of Prince-Weiss, is going to give us a presentation on optimization of microcellular foam molding technology. Let's welcome.
Thank you. So firstly, I'd like to say thank you for Yitzumi. Yesterday, we signed an agreement together to develop innovation in Europe and in China. So that was a very exciting development. And what I'm going to explain to you today is about an activity that we've been working on to maximize foaming technology. So an introduction. So, as you know, my name's Michael Prince. I've spent my whole career in automotive plastic engineering. So as a supplier of plastic parts to the big OEMs, and then I joined Toyota 10 years ago, and I worked with them to industrialize and develop new technologies in plastic. My partner, Alex Weiss, is the owner of company Wirmat. They are a leading manufacturer of aluminium tools for small to medium-sized production and prototype. And Yitzumi, the world leader in injection and rubber, as we can see from today's amazing open day. So together, we will create a technology center in the heart of Europe. It will be open in 2018. Prince-Weiss is an environmental plastic innovation center. The foundation of this company is built on passion, innovation, simplification, and standardization. Now, passion and innovation and standardization are very common words, but simplification is the key to maximizing profits. So what do I mean by simplification? I mean simpler designs. I'm talking about simpler processes, reduced bureaucracy, changing standards, changing a lot of things in the industry based on foaming technology and innovation. The environment. So obviously everybody knows the environment is very, very important, but I now feel that we're on the threshold of something really major. And I think that the engineering possibilities for the environment are very exciting. European innovation. So our company wants to actually just industrialize innovation that has an environmental background. So we're not starting from the beginning. We're taking something that exists, and we will support to develop this into the market. Cost reduction. As we all know, cost is the #1 driver of any change. And the activities that we do have to have a cost reduction, and quite a sizable cost reduction, to really make an impact and to go into the industry. And quality improvement. You know, reduced cost doesn't have to mean poor quality. And this is one of the things I'll explain now. And of course, trust and respect. You know, as we work together with Yitzumi and our partners, having mutual agreements, working together towards the same goal, and trusting and respecting each other's work. So, foaming technology. I'm sure most of you are aware of the technology, but it's basically a supercritical fluid, either nitrogen or CO2, is injected into a modified screw. When you inject the plastic into the mold, you have a low pressure, and this starts the foaming process. Okay? As you can see here. So one of the advantages of the foaming process is you don't have what we call the second pressure. Normally when you inject plastic, you inject 99, maybe 100% full, and then we need to put high pressure to stop the shrinkage effect of plastic. And a lot of what we do in the industry is based around this problem. So it takes away that issue. So we have cycle time reduction, we have a density reduction from the bubbles, and we have a weight reduction. So part design injection process, tooling material are determined by one key factor. This is shrinkage. Everything we do in plastic is driven by shrinkage. So let's take a look at the impact that shrinkage has on both conventional and foaming process. So you see here, a common problem we have is sink marks. So because of the shrinkage and the flow lengths, we have an issue with the quality for visible parts. So the effect on the part design is that we need a rib-to-wall ratio of maybe 30%. We have to have special tools to demold and the doghouse design. The impact on the injection process is we have high pressure and we have a longer cycle time. The impact on the tooling material, we need high quality steel to inject plastic. Now, if we take a look at the foaming process, so we don't really have the sink mark issue with the foaming process because the pressure is uniform from within the polymer and is pushing out. So without that issue, we can change the design of the product and we can simplify. So this is the same section of part showing the simplification of the tool structure, but also the ability to reduce the general thickness of the part. And that's where foaming has its big advantages. So the impact on the injection process, we have low pressure, and we have a cycle time reduction. No second pressure reduces the cycle time. So the impact on tooling, lower pressure allows us to use aluminium. And this is one of the key breakthroughs that we're going to explain today, which has a huge impact. So maximizing the benefits of the foaming technology. Foaming technology allows us to change every aspect of the injection molding process, from the material to the finished product. Prince-Weiss are focused on maximizing this benefit. So our targets, from a material point of view, we're looking for low density, good nucleation. We're looking for bio-based and low cost. For an injection machine, we need low energy, low cost, and high quality. Part design, we want to design lightweights from the beginning. This is also very important. From the tooling structure, so we want low cost, we want short production lead times, and we want improved productivity. From the texture point of view, we're looking at improved quality and reduced lead times. And I'm glad to say that my friend here, Steve Aaron from Etchman Textures, is also supporting us with the specialized coatings that we're going to use for the solutions I will show you soon. So injection pressure, we want the best process for cycle time and quality. So that means low pressure, low temperature, and quicker cycle times. So the realistic advantages you can expect from this type of activity, and when I say realistic, I mean these targets have been reached and are in mass production with the technology that we're doing. So you're looking at a part cost reduction of about 30%. You're looking at tool cost reduction of 20%. You're looking at a weight reduction, 30%. And you're looking at a cycle time reduction of 40%. And when I say together, we have the team now to really push forward these ideas with Yitzumi, with Etchman, with GK Concept. We have a team together that will be able to maximize the benefit of foaming. So, temperature is a big concern for foaming. And when I started looking at this activity of Musal, maybe 5 or 6 years ago, I realized that one of the big problems they had was the issue of temperature. What happens normally is, if there is heat remaining inside the plastic, when you open the mold, it can keep expanding. We call this phenomena post-blowing. Here is an example of what we call a HVAC unit. So this is an engine part, polypropylene part. The supplier wanted to try the foaming technology. So he took his existing steel mold, he sent it to a factory, they injected the foaming technology, and the result was bad. So they had actually an increase in their cycle time, and only maybe a 3 or 4% reduction in their weight. So they give up. They say, okay, this technology doesn't work. But it was a mistake. Their mistake was they didn't design the product, and they didn't design the tooling for the process. And this is the most important thing. When we look now at the solution, so using aluminium. So what I realized early on was, why do we use steel? What is the purpose of using steel? Steel is used because of internal pressures, maybe corrosion, but what we have in aluminium is a massive reduction in the cooling time. So we are reabsorbing the heat much faster than steel. And the fatigue limit, if you look at the pressure inside the cavity between between solid injection and the Musal, it's a massive difference. And it means that when we use the highest grades of aluminium, we are not breaking the threshold of the fatigue limitation that is normally associated with aluminium tools. So, how do we implement this technology? The biggest issue we have in the industry is we all have great ideas, technologies, but it's very hard to convince people to actually make the change because there's a risk involved. My background from working with Toyota, very conservative company, it was difficult to make a breakthrough. So we had to find a strategy to do this. There we go. So step one, what I decided to do was, let's look at existing products. Whenever you try to introduce a new technology from the beginning of a project, it's very difficult because the lead time is short. And they always say, no, lead time is short, we don't have time to do this. So you take an existing product, which is what I did. I took an existing part, I redesigned that part for Musal, and I made an aluminium mold. I proved that the quality was okay, and then we swapped production. So step one, take an existing product, redesign it from Musal aluminium. Step two, visualize the weight and the cost saving. And step three, create the activity plan and the schedule to push it forward. So here's an example of what I call a running change, okay? Swapping the current production with a Musal aluminium replacement. So this is actual results that we had on one product, a polypropylene part for automotive. And if you look at the cycle time, so 60 seconds for the solid part, 30 seconds for the aluminium. So we have, of course, 120 parts an hour instead of 60. The machine hourly rate is only between 5 and 8% more because, of course, with foaming technology, there is some investment. The injection molding machine is slightly more expensive because we have a special screw and you need to buy the gas unit. But if you amortize the cost properly, it shouldn't be a factor to stop investing in this technology. The tool cost in steel was 180,000 euros. In aluminium, we made it for 150,000 euros. So we had a volume of 1 million parts in total, spread over 5 years. And you can see that the material cost for the solid normal part was 2.8 euros. The cost for the Musal aluminium was 1.8. And the reason is, if you look at the part weight, 1,400 grams in solid and 900 grams after we redesigned the product and we changed to Musal. So the production cost was much lower because the cycle time is much faster. So even with a small increase in the hourly rate, it's not really an impact at all. So the total cost for the life of this one product, plastic part, it was saved 1 million euros from its lifetime. Now, when I look at the investment that we had to make for the tool, that was paid back in 10 months. So that means when you go and you say to a supplier, listen, we can implement this technology in a risk-free environment and you can have your money back quickly, they go for it. They want the weight reduction, but they want the cost reduction. And this type of what I call running change is a one-time activity just to give the confidence to the supplier that everything is okay. So A-surface quality. One of the biggest blocking points with foaming technology is the poor A-surface quality. So normally Musal parts are foaming parts are either non-visible, underbody parts. So we are working with Edgeman Textures. They have a process of a ceramic grain, and this changes everything. What happens normally is that when the plastic hits the steel, there is a thermal shock, and that normally creates not a solid layer, more like a membrane, okay? and the polymer runs inside that membrane. What happens with when you have the nitrogen, it's exploding out the front of the melt, and the debris is trapped between the steel of the core and the plastic layer. When you add a ceramic layer on top, just during the injection phase, it stays liquid because you can't absorb the heat, it's ceramic. That is enough time to reabsorb the defect and give you a very high quality A surface. So we have actually had products that we have put on with this technology, graining, and the quality is amazing. I mean, it really is very high quality. So we know now we can solve that A surface quality issue, and if we are mainly focusing on polypropylene large parts. This is where we get a big maximization of the aluminium and the ceramics. You know, if you tried to use glass-filled nylons and this, it would damage not only the mold, but the ceramic itself. So but PP is a huge market. So here's an example of one of the activities we did. So we took a backdoor trim. It was 1,800 grams, and you can see the texture here is like a green texture. So it looks a bit strange. We ended up with a weight reduction of 594 grams, which is a 33% mass down. Now, we did that not only from the foaming, and this is the point of view. The foaming allows you to change everything else. So 4% was only by the bubble, so what we call the density reduction by bubble. But 17% was by design. Because we don't have the sink mark, the ratio between the A and the B surface doesn't need to be 30%. So we reduced the wall thickness of this product from, I think it was 3 millimeters to about 2.4, something like this. So the foaming allowed us to do that, and that was the key. We had a reduction of 12% by changing the material. So earlier when I said challenging all the standards, you know, the company had a mineral-filled talc that they insisted was necessary for this product, but we found an unfilled polymer that could nucleate well, and it passed all testing and evaluation. So that wasn't a blocking point. This is the challenge. As I said, we have 20 tools in mass production using Mucell with aluminium, and we're accelerating now with the A-surface quality activities to go forward. So know-how, you know, there's a lot of questions about, okay, so foaming technology, how does it affect? So what you have here, I think one of the biggest impacts is tensile strength. That's the tearing of the polymer. So you have quite a big reduction, maybe 30% in tensile. But in automotive and many other plastic parts, tensile strength is not the blocking point. So yes, it's a drop, but you design around this issue. And as I said, the majority of parts, it's not such a big issue. Tensile modulus, the flexibility of the product, can be slightly higher. We're looking at impact at 23 degrees, a little bit lower, and the impact at minus 30, again, a little bit lower. But the key thing with the foaming technology is you have to change every way of thinking how you design the parts. Do you add more ribs? Do you add less ribs? There's a lot of know-how that goes into how we design to make sure that we can change these. You know, this is the result from doing tests on just small plaques, standardized tests. The reality of on a real product can be different, and we know this. So, to avoid corrosion and fatigue, which are really the two biggest problems with aluminium, material selection and tool part design are key. So, for example, you know, you're looking at designing your product, you don't want to have a very small shutoff angle. Aluminium rubbing together is not a good idea. It's not a good idea with steel. The tool material selection. So we have protective coatings. We have improved venting. We have high grades of aluminium we are using to avoid these problems. And part design. You don't want to have thin steel. You don't want to have complex parting lines. And you want to avoid low shutoff angles. Know-how is critical for this. I mean, we have been developing now 5 years, and we had a lot of learning along the way. But we can tell you that this works, and it's in mass production, and it's becoming very successful. So, thank you for allowing me the time, and it's a pleasure to promote to you.
Thank you.
Okay.
Thank you very much, Mr. Prince.